So in the last video, we talked about mass spectrometry, and we said that it gives us mass. Hey, how easy is that for a test question? And it gives us mass of compounds or fragments or isotopes. All right. So what I want to do is I want to kind of just touch base on this isotope concept again before we go even further, because it's kind of important, right? I want to make sure that you understand this whole concept of isotopes and how they play a role. So there's two isotopes that you might see in a analysis, and one of the most commons are carbon-12 and carbon-13. Now there's a couple of ways that we can write these. This is one isotope way that we can write them. We just write the symbol, and then we write the atomic weight to the side of it. So that's carbon-12 and carbon-13. Now the other way that we can do this is that sometimes in the symbols and the notation of an isotope, we like to put the focus on the weights, and that's why we're seeing it there. So what we do is that we can also write it this way, carbon-12 and carbon-13, but just to drive home a point, we can also write a small 6 down here at the very bottom. This small 6 is the atomic number of carbon on the periodic table. The atomic number is not changing. That's why we're writing it at the bottom, because that is not really where my eyes look first. My eyes typically look up here in the top left-hand corner. We want to put priority on those. So carbon-12, carbon-13, and small 6s sit down below just to fill up this proper isotope symbol that we might see. Okay? So there's two different ways to represent an isotope. Keep in mind, proton numbers are the same. That's why those are not changing. The electrons, even if they did change, who cares about them because they don't weigh anything. And this is coming from extra neutrons. It's gained 1 to make it a 13. So they've got the same chemical properties. They have the same atomic number. No difference in them at all, except for the weights of the compound. That is it. Or really isotope in this case. Now, I also told you that on the periodic table, you have these weights that sit down below. So, for instance, carbon has a weight of 12.01 on the periodic table. And we said, or I said, that people were lying to you this whole time. That 12.01 is not the weight of the atom. That is the average weight of all of the isotopes and the abundances that show up. That's how they're getting those numbers. Meaning that every single carbon does not weigh 12.01. That is the average weight. Some carbons you're going to have weigh a little bit more. Some you're going to have weigh a little bit less. Some will weigh extremely much more. But that is the average when you look at all of the isotopes that particular atom will have. A lot of people are thrown for the loop, but that's the way it is. So here's a chart, and this chart will list my carbon-12 and my carbon-13. And here's the mass numbers for each one of those specific isotopes. So this carbon does weigh 12. This carbon does weigh 13. And then down here at the bottom, these are the relative abundances. Now, this was done by Shimatsu. Shimatsu is a Japanese company, so I don't know what an abundance is, but that's probably a typo right there. So that's an abundance. They're writing 100, but it's not really 100. This is more like 99.99% of the time. Okay? So 99.99% of the time, I'm going to see carbon-12, and then about 1% of the time, or a little bit less, I'm going to see carbon-13. So what they do is that they use both of these to tell a story. If you look over here in the picture, you're seeing that carbon-12 is mainly the one that shows up. If it was just carbon-12, then carbon would have an even atomic weight, or something close to it. But every now and then we see basically a carbon-13 sandwiched into the picture 1.8% of the time. what's going to be present. So let's do a calculation. We're going to do 0.999% of the time, we're going to have carbon-12. All right, so I just multiplied those two numbers together. I got 11.988. And then I'm going to add to it the other version of carbon that can come around. So 0.00108 times 13. And then I'm going to hit enter, and I get about 12. Well, on the periodic table, it's 12.01. All right, so let me kind of expand this out even more. 12, see if we can get something closer, times 0.999999 plus 13 times 0.00108. Look at there. 12.01. That's the number that shows up on your periodic table. So again, that weight is determinant on the abundances of all of the isotopes that these atoms can come to you in that particular form. So now that we have this concept of atomic weights, knowing that isotopes are present, knowing that these isotopes will have slightly different weights, even though it's carbon, carbon can come to us in multiple forms. Oxygen can come to us in multiple forms. Hydrogen can come to us in different forms. There's deuterium, there's tritium, right? We've got different isotopes for everything. We now can go on and talk about what's going to happen in the mass spectrometer. So, let's say that I have a sample, and I insert the sample in the MS system. Now, keep in mind that what's happened before that we're not really talking about here, I'm kind of starting in the middle, is some separation. So maybe the GC portion has already happened. Maybe the HPLC portion has happened. The ICP portion's already happened. There's some separation that has already taken place prior to this step. So from this point, we're going to say that it is kind of a pure sample that we are injecting. This has been separated out from the mixture, it's been isolated, and now it's getting injected on the MS system. Once it goes into the MS system, two things have to happen to this sample. Number one, it has to be vaporized. And number two, it has to be ionized. Ionized is not the same as an isotope. Vaporized basically means we got to make sure it turns into a gas. That's going to be the best option for the mass spectrometer, which is why the HPLC systems are a little bit more expensive. The HPLC system works under liquids. It's typically a liquid by the time it reaches to the mass spectrometer. There's an extra piece that's got to take that liquid and turn it into a gas, so that way it can analyze it a little bit better. Not only that, but when we talk about vaporization and we talk about gases, then what this leads us to do is boiling points. So boiling points are very important. We kind of have to know what we've got. We have to know what range of boiling point that we have for our compounds, because we have to make sure that they stay as gases. And if they do not stay as gases, then this will lead to contamination. We can get buildup on the front end of the mass spectrometer because that liquid is still staying behind. And unless we drive that liquid off, nothing's going to happen. It's going to constantly give us contamination from point A to point B. So boiling point is very important. As far as ionization, well, what does that mean? Then that means that these things are going to give us some type of charge. Charged molecules are created in the system, and they have to be charged in order for the machine to work. So in the very beginning of this instrument, we have this pure sample. This pure sample has to be turned into a gas in order for it to go forward. And then the pure sample has to be ionized, meaning it has to get some type of charge. Now, the question is, what type of charge is it going to get? And how does it get that charge? We've got to do something to it. All right, so here's my little molecule. And it goes into the entrance of the MS. And here we go. One of the most common ways for this compound to become charged is I'm going to send an electron beam through it. This is kind of where the term spectroscopy comes into play. Remember, Thomson and his cathode rays, they were electricity. They were energy beams. We could do things with them. Light bulb in a UV, the energy beam in the infrared, the light bulbs in the AA. Well, here's our electron beam. Think of this as kind of like the spectroscopy component of the MS. So this electron beam is going to slam our compound with some energy. This is the most common type of beam that we have in the MS system. And because of that, this is going to be called EI, Electron Ionization, or Electron Impact. Either one of those are okay. So electron I stands for ionization because that is where we create an ion, or I can also stand for impact because that's exactly what it's doing to our molecule. So you have to think of this electron beam and the molecule getting into a fight. And the electron beam is going to come in like a big bully, and it's going to punch the crap out of that proton or out of that molecule. And when it punches, this poor little molecule can lose something. And what it can lose is an electron. And what we're left over with at this point is our compound that's now a positively charged. That electron is the tooth. Away it goes. You'll never see it again. And now we've got a toothless little compound that comes into the machine, as ugly as it might be. It's coming into the machine and it's wanting to get analyzed. This is the first step to the mass spectrometer system. Now, this energy beam's very specific. We have to keep things kind of constant. We don't want too many variables going on in the mass spec systems. So what does that mean? Well, these electron beams are based on 70 electron volts. That is the amount of energy that we're basically slamming the molecule with. We never really want to change that number. All of our databases, all of the mass spectra that we begin to generate and that we begin to reference, they're mainly based on 70 electron volts. So if you go to the SDBS system, the spectral database system, this is where you have been pulling maybe some infrared spectra. There's also an MS category that's going to be listed there in that table for you to choose from. That MS database is all based on 70 electron volts. Now, this can change. The 70 electron volts can change, but we're changing it for research and development purposes. There is no reason to change it for anything other than that. As far as the electron beam goes, the higher the energy, that's more teeth that get knocked out. We necessarily don't want that to happen. It complicates things. If we lower the energy, then sometimes we don't knock out teeth. And that might be good. But the problem is that this leads to very simple MS spectra. And sometimes it doesn't tell us all the information that we need to make a decision. So 70 is going to be the Goldilocks number here. All right? Anything lower, it works. We just might not walk away with the information that we need. Anything higher, it works, but we might walk away with too much information than what we need. So 70 is going to be kind of the prime sweet spot for the electron ionization or electron impact method of the MS. We have a special name for this thing once it forms. This fragment with a positive charge, this fragment is typically called a radical cation. Cation because it is a positively charged species. Radical because in chemistry, hopefully what you have learned is that an atom, let's just say an oxygen, could have a pair of electrons. And this pair is typically staying together every time. They're best buddies. But every now and then, we can get a split in that pairing. And only one electron can get removed. And this is what we would call a radical. It's not paired up. Well, that's one term that we can use. Another term that we like to use, though, to talk about the same thing is called a molecular ion. So the sample comes into the MS chamber. The sample gets hit with electron ionization energy, and that sample is creating or will create a molecular ion that eventually will become analyzed. This is what the MS is seeing. If the ion does not get created, the MS does not see it. It has to have the positive charge. It's got to, or it will never reach the point of detection. All right, so that's where I'm going to stop this video. We're getting kind of in the beef and potatoes of it. So we'll continue on with this theory in the next video, and we'll talk more about how this instrument's doing its job. And then what we'll do is that toward the end of these numerous videos, we're going to start looking at spectra and beginning to analyze it. So right now we're just focused on pieces and parts and what makes this thing work.